Okay, but now to the next task. We want to get the particles out of water. We've got green and red flocks and particles going up through plate settlers, and we'd like to capture as many of them as we can and send them back into the flock filter. So we're going to explore plate settlers. And to do that, we're going to build up. We're going to start with the simplest of systems. And that is what was the kind of tank that was built first by humans. Just a big tank that has flow moving horizontally across it. So a horizontal flow sedimentation tank where the water enters at one end of the tank and exits at the other end of the tank. And then you're hoping that particles settle out. Okay, so let's just do a little bit of math. How much time is required for the water to pass through the tank? Well, if we have a certain flow rate, and we know that this tank volume is W times H times L, if we take the tank volume and divide it by the flow rate, we get a time, theta. Okay, that's how long it takes for the water to move through the tank. How far must a particle fall to reach the bottom of the tank? And to do this, what you do is you consider the worst case scenario. So which particle that's entering this tank has the furthest to drop to get all the way to the bottom? Well, it's the particle that starts at the very top, and it's got to find its way all the way to the bottom before it gets to the other end of the tank. And so it has to drop a distance of h. And it's got to drop that distance h in time theta. Otherwise, it's not going to get there. Got it? It's got to drop distance h in the time that it takes for it to cross the tank. So how fast must it travel? Well, it has to travel at what we call now the capture velocity, which is a property of the tank. And it's given this tank and how fast the water is flowing through the tank, how fast does a particle have to drop in order to be captured? So the capture velocity is equal to h over theta. And we can then just do some fun with this equation and then have another insight. So we're going to get rid of theta, and we're going to put theta is volume divided by flow rate. So I put that in there. Theta is volume over flow rate. And then we're going to get rid of volume, and we're going to put volume is length times width times height, and the height cancels out. And so we end up with Q over LW. And then we have this amazing insight. That's equal to Q divided by the plan view area. You see that? It's Q divided by the plan view area. And that means that all that matters for your sedimentation tank is the plan view area. Oh, and depth canceled out. Is it kind of surprising? Depth cancels out because if you increase depth, the water moves more slowly across the tank, but you also have more time for the particle to get to the bottom. And those two effects are exactly the same. So if you're going to design a sedimentation tank, given that equation, what are you going to do? Yeah, basically you take a cookie sheet and with a tiny lip around it, and you've got the perfect sedimentation tank. Can anyone see one thing that would go wrong if you had a cookie sheet? You know, a cake pan that's only 1 centimeter deep of water, okay? And you got water flowing from one end of the cake pan to the other end. Can you imagine any failure modes when you do that? This is the fun of engineering. Because if you can figure out what the failure mode is before you actually build it, it's better. To fill up with sediment, and there was, because it's a really shallow tank, it's not going to take long for sediment to fill up, and then something bad's going to happen. Can you imagine, like what do you think is going to be bad about having it fill up with sediment? Like what else is going to fail as it begins to fill up with sediment? Like if you were measuring turbidity at the effluent of this tank, what do you think would happen as it slowly fills up with sediment? Or we have mass conservation, so we know that the particles are going to go somewhere, and we're like, but there's no more room in the tank. So your logic that they probably end up in the effluent is good, but then it's fun to go down the path of, well, why? Like what actually makes it so the particles get transported to the effluent?
Is it because sorry, it's because
No,
the
go ahead.
water's moving faster because now it's shallower and shallower, so it's moving faster. It's just carrying everything straight across.
Yeah, the engineering term would be you've reached scour velocity. So just like a stream carries sediment down the stream by scouring it along the bottom, it means that there's enough shear on the flocks to transport them horizontally. You could do the same thing with sand. If you have water flowing over sand, once the velocity is fast enough, it'll start moving the sand bed along. And you could think about sand dunes as something where air was actually scouring the sand to move it along and have sand dunes move. So we've demonstrated that this is bad if it gets too shallow. And so we now realize that there are other things that matter besides just the plan view area of a sedimentation tank. But we do have this one cool insight. Plan view area is what matters. And if we build a sedimentation tank like this, it ends up that the plant or the tank ends up being pretty big. You could do, yeah, okay, forget the math. Just take it, it's big. And so we're going to want to see if we can figure out how to make this smaller so it's more cost effective. So we're gonna one more insight here. Will this tank remove any particles that settle slower than the tank's capture velocity? Is there any particle that could find a way through this tank where it would land on the bottom, even though it's settling slower than the capture velocity? Maybe you have to make some more assumptions. Let's assume that particles are actually effectively being injected all along that entrance face. So one face of the rectangle, somehow we've made that whole face be maybe perforated with orifices, with holes, and there's water flowing through that entire face. Now, can you see a path that some particles could make it to the bottom? Because the particles that enter near the bottom of the tank don't have to fall very far. So with a horizontal flow sedimentation tank, it does capture some particles that are settling slower than the capture velocity of the tank. So there it is. That particle that we caught was settling slower. We still caught it. And so that answer is yes. Question? Vertical flow tanks. So now we're going to change the geometry completely. We're going to have the water entering from the bottom face of the tank, and like this immediately has some problems, right? Like, well, where's the sediment go in this case, right? But bear with me. So we have water entering at the bottom. How long does it take for the water to pass through this tank? Well, it's going to take the residence time of the tank, theta, again. So that was easy enough. Now, this one's a little trickier. How far must a particle fall relative to the fluid to not be carried out of the exit? So in that time theta, how far must a particle fall in order to not be carried out? It has to fall exactly as far as the water went up. So during that time, the water went up a distance h. So the particle, in order to not be going up, has to be falling a distance h. So we've got to fall h in that time. So guess what? It surprisingly is the same equation. The capture velocity is h over theta. We can do the exact same substitutions we did in the last slide. And we have that the capture velocity is the flow rate divided by the plan view area. Kind of cool, kind of confusing. So now we have, this is just the way it is. And one way to think about it is it's the bottom of the tank that is where things can settle out on. It's what gravity is acting normal to. So that's what we need more of. We need more place for flocks to be able to settle out, more area for them to settle out. And that's what determines how effective this is going to be. And so then you like, well, why don't we go back to this system? Why don't we just put 2 cake pans on top of each other? Why don't we just make a bunch of small tanks and have them on top of each other? Why wouldn't that work? Right, because if I have a whole bunch of tanks stacked on top of each other and I have water flowing through each one, then I've effectively increased my plan view area. But the problem is I have to figure out what to do with the sludge. Sludge is the problem. See, Cornell University has a water treatment plant that was built in the 1920s, I believe, and it's still rolling along. And it's got a horizontal flow sedimentation tank. And that sedimentation tank is probably like about 4 meters deep, like 12 feet deep. And during the course of the year, and especially when there's a really turbid, when there's runoff in Fall Creek that they're using as their water source and the water is really turbid, that sedimentation tank begins to fill up. And so every 6 months, when students are on break, they take down 1/2 of the sedimentation tank. They go in there with fire hoses and they blast it out, and they have a drain that it can go down, and it goes out to some lagoons. And it gets deep. I don't remember how deep it gets, but I think it may get like 8 or 9 feet deep of sludge, a lot of sludge. Okay, so if we had a bunch of shallow tanks, that becomes more problematic. And if we're going to send humans in there to clean it, then it has to be kind of 6 or 7 feet tall so that people aren't complaining. And all of a sudden, it's not so shallow after all. So it feels like we're going down a non-productive path, right? Having a bunch of tanks stacked on top of each other is not the great solution. And instead, we're going to invent plate cellars. We're not going to invent them. They were invented a long, long time ago, but we're going to use plate cellars.